many users actually use finite element software like Abacus, like ANSYS. In fact, on this channel, a lot of my audience watch how I use Abacus. But one question that often comes to mind is, what is really going on within the software that you're using? Do you understand what the principles, the implementations, and the thinking behind the developers of this finite element solver? If that's what you're looking to understand, then sit back and relax as I walk you through what's really behind the finite element modeling software that you use. So welcome to this channel. My name is Dr. Michael Okereke. I'm a university lecturer and associate professor within a UK university, and I teach extensively finite element modeling within my university, and I've also authored a book which is called Finite Element Applications. And within that book and within my modules, I teach people extensively what's going on within most finite element software, not just from a user's point of view, but also understanding what is going on within the brain of this RVEs software that we are used to. If you've been watching on this channel, you would have seen that I use extensively Abacus, and I've never actually delved into what is going on deep in the heart and the brain of Abacus. So in this video, that's what I'm going to sort of unpack to show you extensively what is going on within the software. And I've prepared a few slides that can walk us through that. So the first thing is, every finite element software has these components associated with it. The first of them will be the preprocessor component, and I will explain this in more detail. And then the second component of that is the simulation engine, and then we finally have got the post-processor component of this RVEs software tools. So whichever tool you're using, you will always encounter these things. And what happens is that the preprocessor stage will always produce a file, usually a text-based files, and this text-based file will normally have different extensions. So in this case, for Abacus, our extension will be a star.imp file. So it's an IMP file. Other software tools will have different extension that they give to their code. But the key thing, the key feature for all these keyword files or input files is that they result from whatever you're doing at the preprocessor stage, and then they become a set of instructions that you give onto the simulation engine. After the simulation engine, you get also another set of files, not necessarily a text-based files. It depends on the proprietary software that the company is developing, and in this case, that output file is usually a set of the solutions from the RVE solver, and from that solution engine, that output file is then passed on to the post processor, and the post processor will then begin to crunch on the numbers and show you the sort of result that you normally will see from your simulation. And this is essentially the backbone of every RVE solver, from processor to simulation engine to post processor. So in the remainder of this video, we'll be focusing on each of these different stages, delving deeper into what's going on, what is really happening within them, so that you can understand what really is going on within your RVE solver. But outside of this backbone, you could also have a possibility of a parametric study. And the sense of the parametric study is usually one simulation may not be enough. You may want to go on an iterative loop. So RVE solvers do also have an iterative loop or a parametric study where you play with the variables in order to get an optimal solution. There are also what I describe as interfacing modules. They are not necessarily part of this framework, but they are modules that could be attached onto the system to make it work better. For example, if you're going to use Python to talk to your code, then that becomes an interfacing module. Sometimes people do connect, other plugins to the main framework in order to simplify the sort of simulation that they're trying to do. There may be also instances, for example, Abacus have got a plugin that allows you to connect Abacus to SolidWorks, so that when you're working within SolidWorks, changes in SolidWorks is automatically updated inside Abacus and vice versa. So if we focus on the first stage, which is the preprocessor stage, and I just want to describe that. So the preprocessor program essentially consists of a set of instructions, a set of activities, a set of programs that run to create a set of inputs required for executing the next step of the finite element process. And what I mean by this is basically at the preprocessor stage, you're trying to generate as much information to advise the simulation engine of what next to do. So for example, if you want a certain final mesh to be executed in your model, that's what you do at the preprocessor stage. You refine the mesh, and then that information generates a new mesh, which then passes that information to the simulation engine. And we take that information to now inform what happens once you get into the simulation engine. The set of instructions or commands or inputs are normally stored within a text-based file, which in this case is called a keyword or input file. And then the final point is that this aspect of the program is usually the one that most users interact with. So if I tell you that I'm very confident in using Abacus, usually what I'm saying most of the time is I just understand I understand my way around how the Abacus interface module works. And in all intents and purposes, that's probably right. Because all you're trying to do is you're trying to instruct the simulation engine how to go about running the simulation. And so when you say I can work with Abacus, I can work with ANSYS, you're saying basically I can work with these integrated development environments, which are called the IDEs. So what are some of the activities that you can carry out at this preprocessor stage? And I alluded to them already before. The first of them is the virtual domain creation. And that's really how you specify the boundaries in space within which the simulation has to happen. So if you're trying to design a damage of a tensile specimen, and again, if you're interested in this is an extensive video I made showing how to undertake damage of a tensile specimen. And so for that, you need to create the specimen. And when you create the specimen, this has to be done within the preprocessor stage. And within Abacus, the section that does this is called the parts. Then the next thing is a discretization. You need to mesh the module because finite element relies on discrete elements. So you need to mesh the elements. And so there has to be a meshing feature within your preprocessor stage. And within Abacus, it's called the mesh module. And then the next one is the material module. You have to instruct the simulation, especially if you're undertaking some kind of mechanical analysis or stress-based analysis. You need to tell the user or Abacus what material module to use to simulate it. And so there is usually a property module within, let's say, Abacus that specifies these materials. And then the next thing that can be carried out at this preprocessor stage is the assembly. The virtual domain is disconnected from the material module. So you could say, I want this to be made of steel, and this material is made of ASTM standard of a tensile specimen. But how would the solver understand that the two of them actually are connected? And so that leads us to the idea of the association module, the way you associate one particular model to a material associated with it. Then we've got also the boundary conditions associated with the FE solution. Every FE solver is essentially a solution of a boundary condition problem. Then there's also a contact mechanism. Some kind of simulation will involve contacts, which need to be within the FE solver. There's parametric studies can be carried out by, again, a module within Abacus called the optimization module. And so that optimizes this kind of solution you're generating in order to improve the sort of outcome that you want. And then the creating of the keyword file. Remember, the essence of the preprocessor stage is to create a keyword file. Once you've done the job and you create the name of the file and you say submit, the first thing that happens is that there is a keyword file that is created. So all these different part of what we call the FE software is essentially addressing the different elements of what we need in order to make the simulation work well. And so at the preprocessor stage, you need to give the user handles to exploring all these different aspects. So if you are liking the kind of content that I'm making, please do subscribe to this channel. We are growing an increasing community of people that are engaged in how Finite Element Solver works. And at the time of shooting this video, we are just over 6,000 subscribers. But I know we can be a lot more because more of you are not subscribed to this channel. So please, can I encourage you, to subscribe to this channel? It does help me a lot, in terms of continuing to spread the reach of the content that I'm making. I know the finite element modeling phase is a field, it's a super niche field, and so we don't expect huge views. But as many as work within FEM, I do want to have a community of people that are engaged with this. So please do subscribe to this channel. I want to increasingly start making content around the finite element principles. And so if you have ideas of principles around the FEA that you think you want some more insight about, please do advise me, and I'll be keen to explore that and see if I can make videos to support my viewers who watch this channel. Thank you for your interest, and let's get back onto the video. So just look at some examples of preprocessor environments that beyond Abacus. Clearly in Abacus, the CAE environment, Abacus CAE is the environment that we are used to, and the audiences that watch this channel are actually used to how I play around with the Abacus CAE environment. So we're not going to dwell on that. But other FE solvers also exist. So for example, ANSYS, which is a common FA solver, it has a preprocessor environment which they call the workbench. And that workbench, one of the modules there could be the designer. The designer helps you create the geometry and make the allocation. So it has a slightly different way of dealing with this. But again, the aim always is to create the preprocessor system. So we have also COMSOL, which is another finite element solver, and it's got a graphical user interface called the desktop GUI, which is also a preprocessor environment. Ultra Hypermesh is again another powerful software tool, and it's got the Hypermesh environment that allows you to pre-process. And then finally, LSDyna is again a finite element solver that is particularly targeted at impact behavior of systems crash, absorption, crashworthiness test, and it's got a preprocessor called Prepost, which is a dedicated software by itself that again helps you pre-process the model and also post-process the model. Before we leave this particular point, the last thing I want to make is that most solvers actually have the pre and the post-processor framework existing on one integrated development environment. So for example, Abacus has got this framework for the Abacus CA that pre-processes, generate the keyword input file, and then you submit the job runs in the background, and then at the end, within that same environment, you post-process your result, you visualize your result, you see what is going on. So it's quite common to have the same integrated development environment being able to do both things. And so the LSDyna pre-post does exactly the same. So it's got the pre and post processor all on the same. So just to study a little bit around the keyword files that we studied. So we talked about the Abacus keyword file, and this is sort of what it will look like. So it gives you a bit of information about the code and the parts, in this case a composite structure, and the nodal arrangement. So what is the node number and the nodal positions in XYZ coordinate system. So this is coming from the discretization. This information then gets passed on to the simulation engine where the simulation will run. Another keyword file is LSDyna. So LSDyna in this case, again, it's got structures. There's the star commands, which are more like instructions for it to execute. So we've got the keyword, we've got the title, we've got control block, viscosity, you've got a material model. This is a user-defined material model for undertaking composite damage. And then also you've got the node like we did before. So again, the node numbers and the nodal XYZ coordinate systems. And all this information again get passed onto the simulation engine to begin to crunch the FES solution. So every solver that you have would have some form of this. You just need to look inside the system to extract what it is. And if you're interested in how to extract these variables, especially for Abacus, do let me know in the comment section, and I could make a dedicated video to show you how you need to do this. So the next stage is the simulation engine. But what exactly is it? Now, the simulation engine is the key machine for the FA solver. The preprocessor stage simply generates a keyword file. Now the actual excellence in the FA solver is done in the simulation engine. It's typically a black box that most users do not actually know about or can change. And like I said, people just engage with the preprocessor and the postprocessor. They don't actually know what's happening in the black box of the FE solver. So when I wrote my book on finite element application, one of the things I set out to do right at the beginning is to sort of grant viewers, readers, insight into this black box of the FE solver. We need to understand what is going on within the FE solver, especially at this simulation engine stage, because this is really critical for people to understand, to be able to interpret their result, and be able to hopefully even develop their versions of their own Abacus FE solvers. So the second point I've got here is that the simulation engine consists a set of proprietary codes, and that means these are obfuscated, these are protected codes that you often will not be able to access or use. And these are developed by the developers of the software. In this case, Abacus, the Dassault system, will be the ones that have written of this code, and they are implemented to help you solve the finite element modeling equation, which essentially is force equals the stiffness matrix or stiffness matrix times displacement. So F equals K is all that we are trying to do when we try to solve an FE equation. And so the excellent way of trying to implement how you go about doing that for complicated problems, quite linear and non-linear, that's all done at the simulation engine stage. The final point here is that most users are not granted access to the specific formulation and implementation of this simulation engine. Yes, it's a black box, we don't know. In fact, if they make it open source, then you obviously will be able to go in and make changes. But we're going to go a little bit more to really peer in and see what's happening, even though yes, it's protected, but what essentially is going on. So the simulation engine solves one simple task. Remember, the FE approach is really to solve an FE equation. So one simple key task of the simulation engine is first to provide the implementation of the direct stiffness method. If you really want me to discuss a bit more around this direct stiffness method, which is at the heart of FE solvers, please let me know in the comment section. I could make video to throw some insight into the direct stiffness method. I have a dedicated chapter in my book dealing with the direct stiffness method. The other thing that the simulation engine can do is that it also helps with the implementation of the Lagrangian or the polynomial interpolation method. There's also the Eulerian method, but most users will often, within finite element and within mechanical engineering where I work, the Lagrangian approach is typically accepted. Most FE solvers will probably be based around the Lagrangian approach. Let's go a bit deeper into what exactly is happening. Beyond just solving those implementation modules that we've talked about, the simulation engine also have bespoke equations, codes that deal with these different elements of your FE solver. So for example, in my book, again, I've got a chapter which I call the mathematics of element formulation, because every element you have in your model actually has a bunch of mathematics that drive it. And those mathematics, if they are based on the Lagrangian approach, they've got a superparametric natural coordinate systems associated with that element. If it's a 2D or a 1D or a 3D element, there are excellent mathematics behind what the element is doing. In fact, it's that mathematics that gives that element its unique behavior. And so within the simulation engine, the developer must find a way of showing how to implement the 1D, 2D, 3D, even higher order elements. And so developers within the simulation engine need to specify how this is done. The meshing algorithms, how you undertake the meshing, and one of the commonest way of implementing meshing is the Delano triangulation. But there are a lot of other ways of implementing this. And if you have a good mesher within your module, it often has a relevance to excellent algorithms developed around the Delano triangulation or other modules, other methods to help you create the best mesh for the model. Material models, so there are obvious material models that exist that you call upon. So whether it's a Hookean model or a plasticity model, whatever the model is, again, that's all implemented within the simulation engine, often obscured from the user. However, Abacus and some of these newer software tools have a module which is called the user subroutine module that allows you to focus exclusively on creating your own material models to drive what you're doing. And typically within Abacus, this is often done within a Fortran code or a C++ environment to allow you create unique instructions for your material that you can bring into Abacus to make the simulation work. Other modules that are within simulation engine is the analysis framework. So these are where you show how to actually make the simulation progress smoothly without the model, the simulation aborting. And so whether it's an implicit model, an explicit model, a numerical method, or Newton-Raphson method, whatever that method is, the whole analysis framework is a set of excellent code, again, implemented by the user to make these things possible. So when you choose a step analysis step, I said I want an Abacus explicit. Someone has done and coded up how the Abacus explicit work. Again, if you consider finite element software textbooks, it tells you the difference between implicit and explicit. It tells you how the time steps has to work, what numerical methods drive in what you're trying to do. And so at the analysis framework, all of that is implemented within the simulation engine. Okay, even contact mechanics that is associated with your model, the interaction module allows this to be possible. So kinematic constraints, again, if you look at my book, you'll find even the kinematic constraints, how that is shown, how that is described. And there has to be a way of implementing that within the finite element solver. So for example, kinematic constraint equations in Abacus is captured when you call a command called star equation. And then behind that, someone has coded up what the star equation command requires, what are the inputs, how it will implement the multi-constraint equations that you need, and how that will have to be applied from one node to another node. There are other modules that are not, uniquely classified like these ones. I just call them other modules. And these are things that help the simulation to run. Finite elements is usually a quite an unstable solution. You're trying to get an approximate solution to a complex problem. And often just solving the equation will not always be straightforward. And so what you then need to do is to find a way to make the model to run. And so there's a lot of model stabilization algorithms that you need to incorporate to sort of help the model to run. I mean, a classic example is when you're trying to do a mass scaling. If you find that your result is not converging, the damage is excessive, and you can mass scale the model. Mass scaling is simply a model stabilization approach. It's not a physical framework, it's quite artificial, but it does help manage with the extreme dynamic energy developed in the system during the simulation. And so it's a model stabilization algorithm, and excellent FE solvers have these implementations that deal with quite dynamic unstable simulation in order to make them stable, and then ultimately you generate an approximate solution that you're happy with. Sometimes you need to incorporate some viscous damping, which is basically artificially damping out the vibrational forces of vibrational energy generated in the system in order to allow the simulation to run. And so viscous damping is another thing that is necessary, especially if you're dealing with damage. I like the part where you can take a programmatic control of what the solver is doing. And this is where Python codes come in, user subroutines come in. So you can write codes that instruct different stages of this simulation engine what to do. So you can interrupt what it's doing at one step, and then it will do that for you. So these are really excellent implementation preparatory codes developed to make the simulation to work well. And they form the framework of the simulation engine. And most of the time, you are not aware of them. Of course, if you have a programmatic control of what's happening, then, writing your programs, you can sort of interface a little bit with what's happening. And if you're interested in how you can program or code up how Abacus works from right inside MATLAB, then this is a video that I've made that shows how you can take over control of an FE solver, in this case Abacus, directly from MATLAB. And that's really this programmatic control element of the simulation engine. So we're going to go on to the third stage, which is the post-processor stage, the last stage of every FEM framework. And if you think about the simulation engine, one of the things you get out of the simulation engine is an output database file. So this is a set of, again, it could be text-based, but not always text-based, that stores instructions of what you have generated from the simulation engine. And then you need to be able to visualize this. Usually these are zeros and ones and text-based problem, and it's not always easy to visualize them. And so we need to have a framework, a module, which is a post-process. The essence of this is to crunch all the information from the output database file and then remaster them in such a way that you can visualize what is going on within your simulation. And the module that makes this happen is called the post-processor module. And usually, like I said before, this module can be also part of the preprocessor, except that you need to call a unique environment to make this post-processing possible. So the point that is worth noting is that the post-processor module is designed to manipulate and visualize outputs from the simulation engine. And so let's look a little bit more at to what the possibilities of the post-processor module. The first thing it will normally do, which we know, is that it creates the contour plot of your simulation. So a contour plot, like shown in this case, showing you the damage of this tensile specimen about the midsection. The next thing that the post-processor module does is it can generate XY plot. So again, if you understand your way around it, you can create instant XY plots. And if this is a mechanical analysis, you typically would want some kind of stress strain analysis, or maybe you just want a nodal temperature across the model, or whatever you're looking for. The sort of graphs that you then need to put into your publication or into your poster, that you can generate right away from the post-processor module. The other thing is that it also shows you video animations. It makes sense to show what animations are going on within the simulation. And within the post-processor module, you can visualize the animations. You can speed it up, you can slow it down, you can section through the model to look more deeply inside to see what's happening. And all that really sort of reflects what's happening in reality. So if you want to see a specimen fell in damage, and you want to compare it with failure type you're seeing from your experiment, then running and viewing the animation of your simulation is really what can help you do that. Then you can monitor variables in the model. So if you're interested in stress, you're interested in temperature, every variable you can switch around in the module to monitor what these variables are and then to carry on with your simulation. And then the final thing that you can also do really is that the post-processor output is really the basis upon which you can make design choices around your FEA. So as part of your design decisions that you're making, for which you came to FEA in the first instance, at the post-processor stage, that's what you're doing. You're looking at it and saying, really like what's happening here. And that's really what this architecture of a finite element solver, that's what is behind your finite element solver. It starts from the post-processor to the simulation engine and then the post-processor. And the framework is all designed to help make it easy for the user to engage and interact nicely and in generating a finite element solution. So if you're interested in learning more about how this framework works, especially sort of output data, the result files, the files that are generated from an Abacus simulation, then I've made this video where I talked about up to 10 file types that you can generate from Abacus. If you have not subscribed to this channel, please can I encourage you to subscribe so that when contents like this are made, you'll be the first to see it. I really am trying to create a community of people who are enthusiastic, excited about finite element modeling, about computational modeling, and this channel is really dedicated to those enthusiasts. And the aim here is for us to help you get to know a little bit more about finite element modeling. And in this case, explore what the framework, the FEM framework is, and computational modeling in general. So if these are things that are up your alley, please do get subscribed to this channel and do leave me comments. I read my comments. I read all the comments and I try to respond to all of them in order to continue to engage and create this community. Thank you for your interest in this channel and I'll see you in the next. Bye-bye.